Today we're going to do some more practice, this time with solving what we would say more difficult equations that have exponentials and logarithms, but really our process is the same. Just like other algebraic equations, sometimes you have to do a little bit more work in order to get x by itself, and that's what we're going to come across today. We're also going to talk a little bit more about those real-world application problems and how our solving techniques can help us with those. So my first thing is, the last video kind of cut off at the end. I want to remind you about extraneous solutions in mathematics. And they are solutions that come out, from all of your work, but then when you go and you plug them back into the original equation, they make that equation false or undefined. So when we had rational equations, anything that made our denominators undefined, we considered those to be extraneous solutions because they were outside of our domain, which means that for a logarithmic function, anything that makes the value for which we're taking the log of, so for instance, I was taking the log of 7, that works. If I took the log of -2, -2 is outside the domain of our logarithmic function, which goes from 0 to infinity. So, our first problem, solve for x. Well, the first thing we want to do is we want to follow our order of operations to kind of clean up this inside part. And in your calculator, if you type in 16 plus 0.878 over 26, we end up with 16.0337692, all being raised to the 3x equal to 30. Don't really know that I'm going to be able to rewrite 30 with a base of 16 point all this decimal stuff. So I'm going to use the natural log method, and I'm going to take the natural log of both sides. And then, because of the power property, I can swing this 3x down in front. And then that's going to be equal to the natural log of 30. So to start getting x by itself, I now have to undo some multiplication, which is not that bad. I'm going to divide both sides by this natural log number. Notice I keep dropping off decimals, but in your calculator, you're going to carry them through. So I get 3x equals, in my calculator, I'm going to do the natural log of 30 divided by the natural log of 16.0337692. End up with 1.2, where'd it go? 226. So then to get x by itself, I'm going to divide by 3. We get 0.409. Now you can always check your answer by plugging back into the original. We know we're not going to have a domain problem because an exponential function can have all real numbers for the domain, but it would be interesting to plug this in and see if when you clean this all up, if you get a number that is equal to 30. All right, so this next one we have a logarithmic equation. So if you remember from our options to solve, for logarithmic we want to get this down to a single log and then use exponential properties. So I have this addition between two logs that have the same base, which means addition can be rewritten using that product property. X times x plus 4 is going to be equal to 1. Well, now to undo a logarithm, I want to rewrite it as an exponential. So that will be equal to 5 to the first. Because of our inverse properties, those are going to cancel, and I get x squared plus 4x, I went ahead and distributed that, is equal to 5. Well, to solve a quadratic, we have a lot of options. We want to start by setting it equal to 0. Factoring, completing the square, we could use a graph, we could use the quadratic formula. This one, luckily, will factor nicely for us. So we get x equals -5 and x equals 1. And again, we should check our answers, especially with a logarithm, because a logarithm has a domain of 0 to infinity. If I plug -5 in right here, already I have a problem, so I've got to throw it out. If I plug 1 in, that'll work there. 1 plus 4 is going to be 5. That'll work there. And I end up with 1. So x equals 1 is our solution. Now, again, it's not because this was a negative number. It's because when I plug -5 in, even if I plug it in here, -5 plus 4 would have given me a result of -1, and that's another way that that -5 shows us it's extraneous, because we can't take the log of -1. All right, so this next one we're going to use log properties again, because to solve a logarithmic equation, we want to have it in terms of a single log. So using that product property, should be an x plus 1 equals 1. So now to get rid of a natural log has a base of e, so I'm going to rewrite this as an exponential. E and natural log are going to cancel themselves out. I get x squared plus x equals e. To solve a quadratic, we want to start by setting it equal to 0, which I'm saying but not actually writing, apparently. Plus x minus e equals 0. I don't know about you, but I could not tell you things that multiply to negative e and add to positive 1. So I'm going to jump and I'm going to use the quadratic formula. X equals opposite b plus or minus square root b squared minus 4ac all over 2a. And if you do this in your calculator, this is really complicated. I'm going to tell you right now, there won't be anything this complicated, but I want to remind you that e is just a number. So at any time, if you come across this, you can use the quadratic formula just like you would if there was a 2 at the end, right? If it doesn't factor, you can still use the quadratic formula. So this actually will work. You do get your answers. One of them ends up being extraneous because it's a negative number, so when you plug it back in, we get a problem. But your final answer is going to be the positive version, plus the square root of 1 plus 4e all over 2. All right, so a little bit easier one. I want you to go ahead and see if you can solve this one. Remember, first you want to try to get your log base 2 isolated using your properties. Pause your video and try it. So I have a lot of work here, but I think this one is going to be the best way to approach this. Best is maybe too strong of a word. The most straightforward way to approach this would be to condense the left side using your product property. And then, because we have log of something equals log of something, those two somethings must be equal, if you remember from the last video. Or you can rewrite each as an exponential, and you'll notice that the 2 and the log 2's cancel out, and we still get to this line right here. From here then, it's a quadratic. We can go through, we get x equals 2 and x equals -3. But if I take 2 and I plug it in, that's fine. 2 plus 2 is 4, that's fine. 2 plus 6 is 8, that's fine. If I take a -3 and I plug it in, -3 already causing a problem. -3 plus 2, still a problem. -3 plus 6, not a problem, but the fact that it was a problem on this left side means it is in fact extraneous. So the other way to approach this one, I did mention before you paused your video to try to write a single logarithm, and so some students might choose to bring this log 2 to the other side with subtraction. Perfectly okay. These two are still going to combine together with the multiplication. Now, because of subtraction, I can rewrite this as a division problem. So when I do this exponential, 2 to both sides, right? 2 raised to the power and 2 raised to the power, these are going to cancel as inverses, and 2 to the 0 gets me 1. To solve this, I'm going to multiply both sides by x plus 6. X plus 6's will cancel, and on this side I get x plus 6, and you'll notice I am right back to this equation. So, your choice on how you want to approach it, but we are trying to get our logarithm to cancel out and rewrite as an exponential. E to the 2x minus 5e to the x plus 6. I see quadratic structure. I see a submarine telling me that a substitution is going to help. So if you remember from substitution back in Unit 8, we have a linear term, e to the x, and we have a squared term, e to the 2x. So I'm going to let u be e to the x. If I square u, I get e to the x squared, which, because of properties, when I raise a power to a power, I get e to the 2x, represents u squared. So e to the 2x is a perfect substitution with u squared. 5e to the x is a perfect substitution with u. Plus 6 equals 0. I can factor this pretty nicely. Minus 3 minus 2 equals 0. Oh, that should be a u. So then I get u equals 3 and u equals 2. But this question was not asking me to solve for u's. I noticed I should use u because of this submarine happening. U was equal to e to the x. So now to actually solve for x, which is what the equation was originally asking in terms of a variable, I need to take a natural log of both sides. Power property lets me swing this one down. Likewise, oh, I wrote, this is where if I was live teaching, someone would have caught me. My apologies. Hopefully you were just cruising, didn't even notice. If I take a natural log of this side, and this side, power property, x natural log of e equals the natural log of 2. The natural log of e says e to what power gives me e, and that is 1. So our natural log of e is going to cancel. Because we started with an exponential, we do not have any domain restrictions, in which case both of our answers are going to work. All right, this next one. We are going to start by factoring. So this term and this term, they share an x. They also share an e to the negative x. And that's about it. So if I take out x and e to the negative x, I'm going to be left with a negative x, right? Because one of these went away. If I take out an x and an e to the negative x, I am left with 2. You can check that by distributing back, and you'll get back to where you started. Well, I've got all these things multiplying together to be 0, which means each one can be set equal to 0. Well, x equals 0, that's solved. E to the negative x. E to the negative x is a reflection of e to the x. That's never going to be 0. And this one leaves us with x equals 2. So, algebra skills, greatest common factor. Still going to help you a lot, even though we're doing more difficult equations. All right, this next one. No way I'm going to rewrite 5 as a base of 2 or 2 as a base of 5. So I'm going to jump to taking a natural log of both sides. Power property says I can swing these things down in front. Now I'm going to try to get x by itself. Well, I've got x's on both sides. So to do that, I'm going to distribute this in first. Using some algebra skills, I get 3x times the natural log of 2 minus 5 natural log of 2 equals x natural log of 5. I can rewrite this a little bit. X times the natural log of 8 minus the natural log of 32 equals x natural log of 5. Product property, bringing stuff up. So now if I get all my x's on one side, all my non-x's on the other side, now I can factor out my GCF. And to get x by itself, I just need to divide the natural log of 32 divided by the natural log of 8 minus the natural log of 5. So that one was definitely trickier. Okay, you got to think about your distribution, think about your algebra skills, how you're going to get your variable that you're solving for all on one side, and then take out a greatest common factor. Last one. The number of endangered animal species in the world from 1996 to 2009 can be modeled by the equation where t represents the year and t equals 6 is 1996. So on a timeline, when we have 6, what we're really talking about is the year 1996, which means that back here at time 0 would be the year 1990. During which year did the number of endangered animal species reach 923? Well, this is going to be the number of species, and this is when. We are looking to find when, which means I'm going to set this whole equation equal to 923. And I'm looking to isolate t. All right, a little flash forward math magic because of our video length, but also you might want to pause it and see if you can do this on your own. I think you can. Solve for t. I worked to isolate my t. I got 16.403. So in relation to 1990, that's going to be the year 2006. Positive, so no need to check for extraneous.